Okay, so let's just look at this. First off, just look at the front page here. And it really should go by pages. So there's 7 pages. So the last page had 35 points here. And that's what it looks like. So that's how many points you got off in the blanks here for each page. So the average was an 84 as opposed to for this exam 2, and for exam 1, it was a 91. So it dropped 7 points. But 84 is about where I like the average to be. The median was 85, and the median on exam 1 was 94. So that was really high, and it wasn't very challenging for some people. So I think it's better to have it more in the mid-80s, the average and the median. And so hopefully that's where it will, I think that's a better level. So why don't I'm going to make sure it's all added up correctly. I'll show you the correct answers. They're also on Compass, and I'll let you out 10 minutes early if you have questions on your own exam. So let me just show you the correct answers so you can look at them. And of course, we grade with continued error. The relationship between these two should be, this should be squared of that one. This should be the square of that one. And this is the correct answer here. This is just notes for if you had grading notes, if you had different answers. Okay, so that's what this page looks like. And if anything's wrong again, you'll have a chance at the end to talk to me about it, or if you have any questions at all. All right, let's look at the next page, page 2. And this one, I don't know if you recognized it, but it was identical to a homework problem. It just had a different story attached to it. And so I think most people did pretty well on it. These were each worth 1 point, but we deduct a point if you circle the wrong if the wrong answer is also circled. So 1 point each for those. Let's turn the page. 4-3. Most people did pretty well on this page. It was very similar to a homework page, to homework problems and practice problems. So this is what it looks like. Make sure it was graded correctly. All right, and page 4 looks like this. Some people got these multiple choices wrong. All right, now the next one. If you are a little if you're surprised to see your score a few points higher than what you saw in Compass. Yesterday I noticed that we didn't grade with continued error properly on this problem. So you might have, if your score is different than what you saw in Compass before break, it's probably because of this problem. We gave you some extra points for continued error. What a lot of people thought for this problem, they somehow thought the degrees of freedom in the numerator, or the degrees of freedom here, was equal to 1. It's really equal to 2. So if you thought it was equal to 1, you would have been looking at a different column here. And so we would take off points there, but we didn't keep taking off here. You would have had, if you put a 1 down there, so that would be continued error. Okay. And here's the rest of it. Oh, a lot of people got this one wrong. I think you just read it quickly. It says if I delete the wife's education from the model, remember this is predicting family income by husband and predicted household income based on wives and husband's education. And so if you delete, that's why there's 3 parameters in the model and 2 degrees of freedom for the numerator. But if you delete the wife's education, well then R squared is going to go down. If they were completely uncorrelated, it would stay the same. But a lot of people chose double I because I think they were used to just thinking, oh, if you add another variable, R squared has to go up. Well, if you delete or stay the same, well, if you delete one, it has to go down or stay the same. It can't stay the same because you already know it's correlated with the Y variable. And this is, if you have two variables that are very highly correlated, you don't want to put them both in the model, like the left foot, right foot syndrome. So that's why this one's circled here. Okay, let's look at the next page. I think most people did very well on this chart. People did pretty well on this page. The only problem, I think some people just didn't get the type 1 error. The Bonferroni correction, remember that corrects for too many false positives. It corrects for thinking there is significance when there isn't, because you're doing all these comparisons, and just by the luck of the draw, even when when nothing's going on, you're going to see some significance. If 5% of them just by chance. So if you have lots of comparisons, you have to adjust from the multiple comparisons to guard against to lower this type 1 error. Okay, and then here's the page where a lot of people got things wrong. This was a little bit more conceptual. This question, okay, this is just the sample R right here. And that was on the previous page, given right here. You could take the square root of that, or you could have computed it, the square root of that right there. You had R squared. So that was the answer there. And what does the area, this little area, represent? Right here to the right of that, well, that's the percentage of the randomized R's that are as big as the sample one we got. And it's also the p-value given by that's the same thing as the randomization test. It's not the p-value given by the F-test. So these were each worth 1 point. And, the biggest mistake that a lot of people made was, I don't know if you didn't read this carefully or not, but there's 10 numbers in each group. So, and you're trying to, it says the group means are 2, 3, and -5. Okay, and the overall means 0. And so you can compute the sum of squares between. And so for each of the 10 numbers in this group, it has the same predicted value of 2, the group mean minus the overall. That's why we're multiplying by 10. Same for this group each. For each one of them, it has a predicted mean equal to its group mean minus the overall mean. So people put 3 here. And I don't know if it was a careless mistake or not, but it should be the number of in each group. Okay? And now these two, if you understand, a lot of people got these wrong. A lot of people put all of the above for both of these. That was the most common answer. Wrong answer. Anyway, sum of squares between equals 0. That means there's no spread between the group means. Between the group means there's no spread. They have to all be the same. They don't all have to be 0. They just all have to be the same. It's very similar to, if a list of numbers has a standard deviation equal to 0, they don't all have to be 0. They just all have to be the same number. There's no difference between the numbers, between the group means. That's what that means. And here it says the sum of squares within. That means within each group. If that's equal to 0, that means within each group there's no spread. So each group has to be all the numbers in each group have to be the same. So there's no spread within each group. All right? Any questions on that? So, all right. So I'll leave this key here on the table. You can look it over if you want. And Again, if you have any questions, I'll let you out 10 minutes early. Hey, if I go over, raise your hand, okay? And make sure that I let you out 10 minutes early. All right, so now we're starting right here on page 119. Page 119. We're starting a new part. And this is the start of the exam 3 material. All right, so we're going to look at transformations of our variables. Why would we do that? Because in order to use linear models for inference, we have these 4 assumptions. And if they're violated, we can often transform the data so that the assumptions are met. Now, the first assumption is linearity, that the true relationship is linear. Now, that's technically not an absolute requirement, but it makes our everything much easier if it's true. So it's often better to it's sort of a rule of thumb to try to make it look linear. So what do I mean by this? So for example, if we just have x and y, and let's just say we're in the positive quadrant here. So, you know, if you just basically have one of these elliptical shaped nice scatter plots like this, well, that's your ideal relationship, okay? That's the ideal, but often it doesn't look like that. So here's x and y. Often it's going to look, there's a lot of common curvilinear patterns that you'll see that you can do transformation of either the x or the y or both and make them look linear. So 2 typical ones, what I've been looking at, seeing a lot recently is because I've been looking at a lot of medical data, is these J-shaped curves. So you have like on the y-axis often is something like, I don't know, death rate or survival, let's just say death rate here. And on the here is something like some kind of treatment. So let's say drug dose. How much drugs are given to you. And it doesn't usually follow a linear pattern. Like if you have 2, so your death rate would be not enough drug, it's going to be bad. It's going to be an optimal. But then often there's like lots of overdosing there too that could happen too. So some kind of curve like that. And if you try to fit a linear model to it, you know, you're going to fit a line that's not going to be appropriate, right? It will look something like that will be your best fit. And so you're going to have these, you're going to overestimate the true death rate in the middle here and underestimate it at the ends. And another one that's sort of the opposite way that you'll see a lot too is, and these are sort of the opposite shape, more shape like, something like that. One of my favorite graphs that looks like this that I've been looking at, there's a lot of data on this recently, is looking at money versus happiness. People's subjective, you know, even physical measures of happiness like stress rates and so forth, but also subjective ratings of happiness. All sorts of ratings of happiness looks like that. So that if you're really poor, obviously, just a little bit of money makes you a lot happier. You know, there's a steep rise. But then, after a while, it just levels off. So even though you get lots and lots more bucks, it doesn't really change your happiness level much. So that's 2. In both of these, this is the ideal. And both of these are bad for, if you try to fit a linear model, a straight line to these, it's not a good predictive line. That's supposed to be a straight line. It's going to underestimate in the middle here, do the opposite, and overestimate on the ends. So sometimes it's harder, sometimes it's actually easier if you look at residual plots. So what are residual plots? We've talked a lot about how residuals need to be independent, identically distributed with normally distributed with mean 0 and the same variance throughout. So that's what we're talking about here. We're going to look at these residual plots more and see what happens when these assumptions fail and what we can do, how we can transform our data. So you look at these residual plots, and if you here, let's just say, so what do I mean by this? All right, so we could plot, for example, here's all the points right on the line have no residual. So we're plotting the residuals, which are just our prediction errors above and below the prediction line, the regression line. So these are the residuals on the y, and you can either plot x or y on the x-axis, either your x variable or your y. But I think it's easier to understand if we do the x's here. So I'll just make it look like this. So I'm plotting x here. And so basically just imagine straightening this out. And sometimes it's just easier to see. You can just read right off with the residuals. And what you want to see is just some random scatter like this, like that. Just want to see a random pattern. I should match it up more to make it look like that one. Okay, that's supposed to be random scatter. And that's your ideal. All right, and everything that's right on the line is going to be right on the line. For example, this point, let's say, that would be like right there. Okay, that's all I'm doing. Now this one, we can do the same thing. So I don't really need that axis there, do I? Why did I even put that in? I'm going to erase that. This is 0. I just wanted to show you this is x along. Whoops. Okay, so this is your x. So here, this would be your drug dose, and these are your residuals. So you can see it's going to look something like that. You don't want to see a pattern like this. That's bad. Okay, you're bad. You don't want to see a pattern. It's bad to see a pattern. All right, and for this one, we can do the same thing. And can I put that in just out of habit? You don't want that there, right? Okay, you don't need it. And so now what do we have? We have dollars along here, and up and down here we have happiness, and now it's just going to look like this. Okay, and that looks bad. You don't want to see any pattern. All right, so now you also want the, there's other ways that you can see a pattern. You can see groupings, and that usually indicates that the x's aren't independent. The errors aren't independent. So one common grouping that we saw could be, let's see, we've seen this type of thing a lot, where you can have two separate groups, like maybe that have positive correlations, like this one, and maybe we could have one down here. So they both have positive, but overall there's a negative correlation like that. And of course that would show up in your residual plot looking the same way as two separate groups. This is an extreme example. We'll look at some examples in a minute. Actual example where it'll see that it's easier often to spot patterns in the residuals. All right? And so this usually shows what? That we don't have a random sample. I mean, if there are two groups that weren't randomly selected, that's why they would look like that. Okay, and another thing is equal variance. We've talked about that a lot. How, so what would be an example where you don't have, so these are both bad, of course. I'm just giving you bad examples, things to check. So here's another one where, what's the most common? The most common, like in our Stat 100 data, we see often we will see a linear pattern, but the errors around here are much smaller, and they increase as X gets larger. So you see this kind of fan-shaped pattern. Do you see what I mean? Like small errors there, but then big errors here. So it would look, you'd see this like fan-shaped pattern. Like that. You see that a lot. And what's wrong with that? Well, one thing is that we're using one standard deviation, a pooled estimate for all across the x's, and that clearly isn't valid here. So this fan-shaped is a very common way that you're going to see problems with the errors. Okay, and of course, the last thing we can check too, besides these residual plots, these are all looking at these residuals versus X here, but we can also just look at a histogram of the errors of the residuals, and we want the histogram to be, I'll just do a smoothed out version of it, to be approximately normal, symmetrical like this. That's what we want it to look like. So that's basically, and any non-normal, obviously non-normal histogram is it's bad because it's bad because our confidence intervals and our all depend, and our tests all depend on those normally distributed or t-distributed, it all depends on the errors being normally distributed. And so and it's bad. We can't apply we can't do inference if it really violates that. Often it indicates outliers that we'll have to maybe figure out why they're there. Okay, so that's the basic idea. You'll understand this a whole lot better when we actually get in and look at real data. But for now, this is just sort of a basic overview. And so what do you do? So if you have these problems, what do you do if these problems show up? Well, there's some classic things you can do that often work. And so if the scatter plot follows a nonlinear pattern, try these steps to make the plot look more linear, to make the errors around the regression line look more normal. And often this will do a good enough job, or will help. So first, look at your y variable. Might as well start with the y variable, because we're looking at, usually there's just a single y variable. There's one response variable, and maybe there is lots of x variables, lots of predictor variables. So you might as well just start with that single y variable and see if it's symmetrical, or if it's not, if it's symmetrical. So let's look at it. So let's say it's symmetrical. Just draw it here. Make it nice and symmetrical, like that. Then that's good. Just leave it. That's great if it looks like that. But what if it looks like really skewed? Like what if it looks like these transformations work only on positive y's? So let's just stick in this. Let's say the y's are positive here. So if it's right skewed, So that would look like a real right skewed would look something like this. And then what you'd want to do to make it look more like that would be what? You'd want to make these big extreme values, shrink them in. So you'd want to do that by, like, let's say, by taking a square root. Like the square root of 100 would, let's say 100 would shrink it way down to 10. And the square root of 25 would go down to 5. So you'd shrink this a lot more than the square root of 1 would stay 1, right? So it would shrink the bigger values more. And even more extreme shrinking would be, taking the log, because that's just looking at the exponent. So if you were taking the log base 10, for example, 1,000 would change to 3, just however many zeros you have after your 1, right? And 100 would change to 2. 10,000 would change to 4, etc. A million would change to 6. So you would just shrink it all down. And an even more extreme, drastic, would be to take 1 over y, but that would also reverse the direction, because the bigger numbers would then become the smallest. It would flip the whole order. So that's not ideal, because it's then hard to interpret. All right, so basically what you can think of this as decreasing powers, because you want to make the bigger numbers smaller there. Or let's say you have the opposite, like our exam scores are sort of the opposite. They look like this more. There's people who got very low or don't even take it and get zeros. But most people do pretty well like this. Well, if you want to make that look more symmetrical, you want to do what? You want to increase these. So you would want to take higher powers. You'd want to spread those out more at the top where they're all bunched in. See? So you'd want to make them out there. So that would be increasing powers. And you'd start with y squared. If that didn't work, you could cube it or even put y in the exponent. Okay, so then what you do is then you look at the scatter plot again with the transformed y and see if it's linear. And if it's linear, then go ahead and you can you do your regression on the transformed variables. If not, then you can do the same transformation on the x variable or variables. And then if the data is straight enough, you fit a regression line, you fit the regression and you find the residuals and you check them and make sure you go through these steps again, make the plots of the residuals, etc. And if everything looks okay and the histogram of the errors looks okay, then you can go ahead and make inferences. So this is just like what we talked about on the previous page. So that's the idea. So we'll look at some examples of both these situations. And that's on the next page. So this is an example of predicting brain weight from body weight. And the data involves 32 species of land animals. 24 of them are mammals, and 8 of them are dinosaurs. So maybe you can, why don't we look at the actual data online? I think it would be easier for you to see. This is, so let's look at this exact same thing on our data program, where this came from, and so you can get a better feel for what's going on here. So let's go to the computer. Okay, so this data set can be found at a different, I don't think it's on the site that our U of I site. It's posted on istix.net. Instead of statistics, it's statistics without the stat in front. istix.net/fireman. All right, it looks the same. It's just I haven't put the data set on our U of eyesight. But this is, you can find it here. All right, so let's choose that data set. It's the brain weight and the body weight of these 32 animals. And let's look at the scatter plot. Okay, so here our X variable from the body weight, we're predicting the brain weight. So this is body weight in kilograms versus brain weight in grams. Now you look at this data and there's 32 animals here, but you can't even see these animals because they're all squished in down here. Like, who are these animals? Like, what's that? That's Brachiosaurus. What's this? What's that say? African elephant, Asian elephant. But there's a mouse. These are a hamster. What's that say? A monkey, some kind of monkey, a pig, a kangaroo, chimpanzee. What else is down here? They're all squashed down here. What's this? That's a human, so you can see that. You can start seeing the dinosaurs here, but that's the Tyrannosaurus rex. These are all dinosaurs. But you can't see all the rest of the animals here. You just can't see them at all. So let's just go back to the notebook for a minute. And so the problem is this, that once you make the scale big enough to see these big giant dinosaurs here, the big animals, and to see the elephants, and once you make the scale big enough, most of the points are scrunched in near zero. All these animals are scrunched in near zero. For both weights, for both the body weight and the brain weight, you can hardly see them, right? You can't. You can't even tell how many there are, and neither can the fitting program. It pays little attention to those small numbers. It's dominated by these big numbers. Yet that's where most of the animals are. So you get this negative correlation here, totally dominated by the slight negative correlation, very slight, saying the bigger your body is, the smaller your brain, which isn't true for most of these animals because it's dominated by these giant dinosaurs here. So you want a transform that counts those little animals just as much as the big animals. Why you want each one to count. And I was thinking when I was doing this, I was reading Horton Hears a Who to my granddaughter. Do you know the story, the Dr. Seuss book, Horton Hears a Who? And so I thought of that bit, and this is a quote from there, that a person's a person, no matter how small. So even though Cindy Lou Who and down in Whoville is tiny, they count just as much. So I thought of that. And so the animals, you want to see all the animals. And you can't. The data program can't. So we want to do a transformation. All right? So let's start and think about our transformation. Go through our steps. Is the scatter plot linear? No, it's not linear. Look at it. It has one arm going this way, one arm going that. And the regression that we fit looks like that. So no. It's not. So now we're going to follow our steps. Why don't we transform the y variable? So the y variable is the brain weight. And here, first, let's just look at the histogram of y to see if it's symmetrical. So here's the histogram of the brain weight. Notice how many of the animals are really small. And then we have a few that are really big. It's up there. Like this is the African elephant, the Asian elephant, the human, etc. So now it's not symmetrical. So this is called what? Right or left skewed. Circle one on your paper. Make sure you get that right. Okay, it's right skewed because the extreme values are to the right. That's called right skewed. So to make it more symmetrical when it's right skewed, we want to bring these in, right? These giant numbers. So what are we going to do? The first thing we would do would take the what? Write it down. So see if you, because this will be like it's good practice on the exam for the exam, or for doing. Just write in what you think it would be. The first step would be try square root of y. And if that doesn't work, that's with the square root. See how it brought them in quite a bit? It's the square root of these. See? Brought it in. It makes it look better. That's the square root. But it's still not normal. Doesn't look very normal. It still has the right skew. It still has that. So now you go more extreme and try the log of y. Now, when I write the log of y, this program says log of y. What we mean is log base e. This is the data program. Most people, when they write logs, mean log base 10, but we're meaning log base e. We're just assuming that all logs are going to be natural logs. So this is the natural log. So our data program, unfortunately, it's easier to say log. So whenever I say log, I mean natural log. If I mean log base 10, I'll say log base 10. I mean, a lot of people, when they say log, they mean natural log, and that's what we're doing here. So I should write this. Our data program, we should write that down. It always, when you're taking a log, it says is always calculating log base e. Okay? It's always doing, it's really always, it should be changed to ln because it's confusing to people. But right now it just says log without the e, but know that it's that. All right? Now, if the histogram were left skewed, what would you want to do? If it was left skewed, you'd want to go up powers. So you'd want to first, if it was left skewed, you'd first try that. If that didn't work, you'd try that. And finally, the most extreme would be to put the y as an exponent up there. All right? So now, we like this one the best. So what we would do is what? Now the next step is, now let's just try the scatter plot. Let's try the regression again. Let's look at the scatter plot. And instead of putting on the y-axis the brain weight, let's put the log of the brain weight. Now let's see how it helps. So we do that. So you look at the scatter plot with the transformed y and see if it's linear. And if not, you try the same transformation on the x variables. Is it linear yet? No, it's not. This is log base e. I should write ln here of the brain weight. Let's look at it here. Let's see. I think it's more fun to do it here. Okay, so we have this. Now, what do we want to do? Look, we have this ridiculous correlation coefficient here. And so we're going to take this y, and first we're going to try the square root. Oh, first let's just look at the error plots, show the errors too. So you can look at these error plots. They don't look so good. Now let's take the square root. Still doesn't look good. Let's take the log. Why don't we take the scatter plot? We don't need the error plots. So this still does not look good. We can see these animals better. There's the mouse, the golden hamster, the mole. They show up. Oh, that was a guinea pig. What was that? That's a rabbit. You see, now we can see these ones. It's better. The mountain beaver. Where'd it go? Rabbit. Cat. Kangaroo. Pig. You see, we can see all those animals. At least they're showing up, but it's still not great. It's not good. So And our correlation now, our regression line is slightly positive, but it's still totally dominated by these dinosaurs. That's who those are. All right, so what do we want to do now? What we want to do now is do the same thing with the x. So let's try square root of x first. Not great. A little better. Now we try the log of x and see how much better that is. Now we can see the animals much better. So we have the mouse, the golden hamster, and there's the regression line. And look at our R correlation coefficient. Now we have this strong correlation of 0.65 from, what was it, approximately negative 0.1 all the way to now a strong positive. So these are the dinosaurs. We've taken the log of both, log base E. These are your dinosaurs down here. Who's this? Tyrannosaurus rex. You see, he's a little smarter than the average dinosaur. He's actually on the line. They all have lower brain weights than predicted by the regression line. Tyrannosaurus rex is a predator, a little bit smarter, had to, be fast and hunt rather than just eat plants. So a little bit smarter. Now here's all these middle humans way above, has a huge residual. These little animals are well below. Who's this? The cat is exactly, see, it makes a good prediction. Perfect for these middle animals here, the cat and the kangaroo, pretty good for these. Pretty good. But these are not very good for these dinosaurs and not very good for these small animals. So if we look at the regression, let's look at the errors. You can see regression, log. And let's look at our residual plots. You can see there's a pattern here. It's not perfect. And it's not perfect. Why? Do you see that there's really two groups of animals here? There's these dinosaurs here, and then there's the mammals. The dinosaurs really are different. They don't seem to have any kind of correlation between their body weight and their brain weight. And they're really two separate groups. So we really should, this shows that we should split the data into two groups or add another predictor variable, whether it's a dinosaur or not. But for now, let's just make the predictions. We did a good job. And let's go back to the document camera. And let's just go ahead and make some predictions as is. So you can see how predictions on transformed variables work. All right, so this isn't good. We transform, it's much better. After taking logs of both weights, we get a plot where all the animals show up, and the fitting routine also sees all the points about equally. See, it sees them all. They're all separate. It comes up with a linear model for the logs with a decent R. See, that's a decent R there. R is much better. I mean, we'd expect a positive correlation between body weight and brain weight among the mammals. I have it written down all the way to lots of decimal places. But the fit isn't great, but it's a good start. So why don't we just work on this so I can just show you how to make predictions on these transform variables. And then next time we can split it into two groups. So right here we said this is a great prediction. Right here just a little bit below the line. That was the cat. But it wasn't so good for us humans. We're pretty far above. So let's look at these two predictions and at the residuals from the regression equation. Here's our regression equation. It says the log of the brain weight is equal to 2.982 plus 0.3190 times the log of the body weight. And you have here your standard deviation of the errors is about 1.565. All right, so why don't we use this equation to make predictions for the cat and the humans and see how far off we are. And this will be very easy for people, all you math majors and people who are very used to logarithms, but maybe people who haven't seen log since high school, who haven't taken much math recently, are probably going to be rusty on this. So let's go through it fairly slowly. Okay, so if the data is straight enough, you can fit the regression, right? So here's the regression equation you just saw. It's the natural log of the brain weight in grams equals 2.982 plus 0.319 times the natural log of the body weight in kilograms. Now, I hope some people I probably should have had them in the same units. My husband saw this before I left this morning, and he said, Ellen, what are you doing? He's a physicist. He said, this is awful, terrible. I don't know, probably some of you are thinking the same thing. You've got to change this. And so I said, well, if I have time, I will. But right now, this is like right when I'm we'll see. Okay, so you understand this is in kilograms and this is in grams, and it might be offensive to some of you here. I'm sorry if it is. But let's just work with it. All right, well, it's a prediction. So we have to say, plus there's going to be some errors. And what is the typical error? Well, we got that. That was the standard deviation of the errors. We should write that down. Our prediction error is this. The typical one, the standard, was about 1.6. Actually, I looked up the standard deviation plus, and it is 1.61. This was just the plain standard 1.565. Anyway, we're just approximating. Okay, so I looked that up. Now, let's use this equation right here to find the predicted brain weight of a cat, given that the cat has a weight of 3.3 kilograms. And this is the cat on the picture. It does have a weight of 3.3 kilograms. So now I want to use this. So how am I going to use this? This is the actual weight. So I'll say, okay, the natural log of the brain weight is equal to 2.982 plus 0.319 times the natural log of the body weight. We'll plug that in, 3.3. Okay? And where'd my calculator go? Oh, well, I have it written down anyways. So I did this, and I got approximately 3.36, rounded to 2 decimal places. Now, that's the natural log of the brain weight. But that's not, I want the actual the predicted brain weight, not the log of the brain weight. So I have to anti-log both sides. So I'll do that. Anti-log both sides just means raise this, take both e to, so it's just, when I take e to that, okay? So e to the log of the brain weight is just the brain weight by definition, right? So I get that the brain weight is equal to e to the 3.36. And now this has no units. This is just, the log is just an exponent, right? But now I'm going to have units here, brain weight, and it comes out to be 28.87 grams. So that is the brain weight of the cat, the predicted brain weight of the cat. All right, let's look at that and see if it makes sense. What did we have first? We said that the log of the brain weight was 3.36. All right. There's the cat. The log of the brain weight, it looks like about 3.36, right? And the log of the body weight would be the log of 3.3. All right, so it looks good. 28.87. Now attach a standard error to that estimate to give an estimated range. Now this is a little bit different because this standard error is a standard error for the log of the brain weight, this standard deviation. So you have to be a little bit careful. I can't just attach that, and I can't just anti-log that either and attach it. What I have to do is watch. So the log of the brain weight, we can attach that. We know it's 3.36 plus or minus the 1.6 approximately. Okay? So what's that equal to? 3.36 minus 1.6 is 1.76. This 2, 4.96. Now these are the exponents. They don't have units. This is the range of the exponents, right? So when I want to get the actual range of the brain weight, I have to anti-log both of them. So I go the brain weight is equal to e to the 1.76 to e to the 4.96. So that's in the exponent. So it's going to be a multiplicative range. It's not going to be your usual, well, you'll see. So you'll get, when you do this, you get 5.8 grams. E to the 1.76 is 5.8, and e to the 4.96 is 142.6 grams. So that is our range. Now, does that look weird to you? Because it's not centered. You can't say 28.87 plus or minus something. You can't do that because that's not the middle of anything. It's not the mean. It's 28. What it is that you can say 3.36 plus or minus. If you take these two together, take the average, it's 3.36. It's right in the middle. But if you average these two together, you don't get right in the middle of that. It's an asymmetrical confidence interval around this. It's not symmetrical around there, so you can't say plus or minus. It's symmetrical around the geometric mean. In other words, if you multiplied these two together and then took the square root, that's what you'd get. So it's asymmetrical. We'll look at that in more detail later, but you have to be a little bit careful so you can't write it as plus or minus something. It's a huge range. It doesn't look so big here, but it's really a big range. Okay, so now the actual brain weight of the cat in the scatter plot is 25.6 grams. So what's the residual? So remember the residual is just the actual minus the predicted. So the actual is 25.6. Boy, we came close. And the predicted is 28.87. So we're just down a tiny smidgen. That's our residual. That's a little residual. That means we have a very good prediction. A little residual. That's a very little residual. And what does that mean? I mean, little in absolute value, it's a little bit below the line. So that means we have a great prediction for the cat. And let's make sure we do. It's just a little, we do. We were almost in the line, remember? It's just a tiny smidgen off. It's just a tiny bit below. Now the human, let's do the same thing for the human. You'll see there's a big residual. Doesn't do as good a fitting job for the human. So now we'll do the same thing for the human. The human is 62 kilograms body weight in the plot. And so we'll just do the same thing. So we'll say the log of his brain weight for the human is what? It's going to be that you just plug 2.982 plus 0.319 times the log of 62. Okay, and I did that, and for the log of the is 4.3. Let's see if that looks right. So this is our prediction for the human. The human's about right there. The prediction looks about 4.3. Yeah. I mean, in that right range. But look how big it is. So it's a big residual. Now, that's the log. Now let's anti-log it. So what's the brain weight? The brain weight for the human is going to be e to the 4.3, which is 73.7. Now we can put our units in grams. And look at the actual brain is much bigger than that. So it's going the human has a very big residual. The actual is much bigger than the predicted. 1,246.3 grams residual. Okay. So any questions so far? Now, so these equations and logs, most people don't, well, some of you probably do, but most people who haven't taken a lot of math classes or aren't very familiar with, aren't immersed in that world, don't think intuitively in logarithms. So it's preferable to switch this equation back to actual units. So we can do that, and we'll get, in general, we'll get an equation that looks like this, and you can see why. So we have this equation. We have the log of the brain weight. Just for those people who aren't as used to working in logarithms. And this is what we have, plus 0.319 times the log of the body weight. And what this says is we're going to get an expression where we're going to get, this is going to be e to the 2.982 times the body weight to this, raised to that. So these, our intercept and our slope are going to become exponents up here when we anti-log. So you can see that. So we'll, okay, so we'll just do it. Anti-logging just means this. All right, so what does that give us? That gives us the brain weight equals e to the 2.982. That's this part right here. We've already got that. And then addition, you know, is an exponent addition. That's multiplication. When you anti-log, right? Those powers are going to be multiplication. So it's e to this, e to the 0.319 times the log of the body weight. Okay, so we can, so this, so here we have the e to the 2.982. Now this is just commutative. These we can just switch the order there. So we have e to the log of the body weight, right? That raised to the 0.319. Now I can, you see that. What is that? Well, that's just the body weight. So we have this, the brain weight equals, that's e to your intercept times e, you know, by definition, this part's the body weight. And there you have your x. And there's your slope. So that's what it looks like when you anti-log it. All right, so now, any questions so far? Okay, so what if we had done log base 10 instead of log base e? What would we have gotten the same equation? What do you think? Yes or no? Anybody know what would change and what wouldn't? Do you think looking at this equation here, this one, like right here, before we anti-logged it. What I'm asking you is if I did log base e instead of log base 10 instead of the natural log, would it look the same? If not, what would change? What would be different? Do you know? Does anybody know? Do you think the intercept would change? Raise your hand if you think the intercept would change. Raise your hand if you think the slope would change. Okay, well, you can see. Let's do it then. All right. So what would change and what would we have gotten the same equation? This is, well, let's look at this. So we have what? Log of the brain weight is equal to 2.982 plus 0.319 times the natural log of the body weight. Now what we have to do is look, what's the relationship between log base 10 and the natural log? Where's my calculator? I know this, but I wanted to show it to you, but I can't find my calculator, so I'll just tell you that, do you know what the natural log of 10 is? Do you know what it is? What if you raise E2 to get 10? Well, so you need to know that fact, right? So basically, if I want to change to log base 10 of the brain weight, I want to change everything to log base 10, you have to know that the natural log of 10 is 2.303. So I'll say you're using this fact, 2.303 rounded. Log base 10 of x is equal to log of x in general. So if I want to change from this log of x to log base 10 of x, I have to divide this whole, both sides of the equation, by 2.303, and then I'll get that. Log 10 base 10 of x is equal to log of x divided by 2.303. So if I divide both sides by 2.303, I will get 2.982 divided by 2.303 plus, and then here I'll get exactly the same thing. It just changes this to log base 10 of the body weight. So the important point is, I mean, you don't need to know this fact. You can do it on your calculator, but the important thing is when you change to different bases, this slope, the important point, stays the same. This is the only thing that changes. The intercept changes. That's all. So this changes, your intercept changes. So if not, what would change? The intercept changes only. The slope stays the same. Slope does not. So this stays the same. That's the important thing. That's why it really doesn't matter which base you're using that much, because we don't really care about the intercept that much. The relationship between them stays the same. So this changes, okay? So that's in general. All right, now let me see. I said I'd let you out early, so I think this is a good place to stop. And you have homework that's due Wednesday night.